Just 4 light-years from where you're sitting right now, something impossible just happened. The James Webb Space Telescope aimed its golden mirrors at our closest stellar neighbour and detected something that shouldn't exist. A mysterious signal appeared in the data. Then, without warning, it vanished completely. Scientists are calling it the disappearing planet mystery, and what they found challenges everything we thought we knew about finding worlds beyond our solar system. But before we dive into this cosmic puzzle, make sure you hit that like button and subscribe, because what you're about to hear might just be the most important astronomical discovery of our generation. When you look up at the night sky from the southern hemisphere, one brilliant point of light outshines nearly everything else. That's Alpha Centauri, and it's not just another twinkling dot scattered across the darkness. This stellar system represents something profoundly special in the cosmic landscape. It's our nearest neighbour among the Sun-like stars, sitting a mere 4.37 light-years from Earth. To put that in perspective, if you could somehow freeze a beam of light leaving Alpha Centauri right now, it would reach your eyes in less time than it takes to complete a college degree. For more than 70 years, astronomers have been obsessed with one burning question about this nearby star system. Does it host planets? The answer has remained frustratingly elusive, hidden behind technical barriers that seemed impossible to overcome. We've discovered nearly 6,000 exoplanets orbiting distant stars using sophisticated detection methods refined over decades. We've found massive Jupiter-sized worlds by measuring the gravitational wobbles they induce in their parent stars. We've detected smaller planets by watching them transit across stellar faces, temporarily dimming the light we receive. We've even directly photographed young, hot planets glowing brightly in the infrared as they orbit far from their host stars. But Alpha Centauri, this system has defied every attempt to reveal its secrets, and the reason why tells us something fascinating about the challenges of studying our cosmic backyard. You might think that being close would make planetary detection trivially simple. After all, nearby objects appear larger and brighter than distant ones. A planet orbiting 4 light-years away should be far easier to spot than one circling a star hundreds of light-years distant. The sheer proximity should provide overwhelming advantages for astronomers trying to photograph planets around our nearest stellar companion. But proximity creates profound problems when you're dealing with Alpha Centauri. The system blazes with such intense brightness that it completely overwhelms the delicate instruments designed to detect faint planetary signals hiding in the stellar glare. Think about trying to photograph a tiny firefly hovering directly beside a massive stadium spotlight. The light from that spotlight floods everything around it, drowning out the firefly's faint glow in an ocean of brilliance. That's the challenge astronomers face with Alpha Centauri. Alpha Centauri A, the primary star in this triple system, ranks as the 3rd brightest star visible from Earth's surface. Only Sirius and Canopus outshine this blazing furnace. When you observe it from dark skies in the southern hemisphere, Alpha Centauri dominates the constellation Centaurus with a yellow-white radiance so intense that ancient seafarers used it to navigate across uncharted oceans. Its companion star, Alpha Centauri B, orbits close enough to create additional observational nightmares. These two sun-like stars dance around their shared centre of gravity every 80 years, sometimes approaching within 11 astronomical units, and other times separating to 36 astronomical units. During observations, the companion star floods detectors with contaminating photons that obscure any faint planetary signatures lurking near the primary. It's like trying to see a candle flame while someone shines a flashlight directly in your eyes from 3 feet away. A 3rd member of this system, Proxima Centauri, lurks in the distant background approximately 13,000 astronomical units from the central binary pair. This tiny red dwarf barely qualifies as a star, radiating less than 1% of our Sun's luminosity. Proxima takes more than 500,000 years to complete a single orbit around the Alpha Centauri system's centre of mass. We've already confirmed that Proxima hosts at least 2 planets, with a possible 3rd world still under investigation. But those planets orbit a star so fundamentally different from our Sun that they tell us nothing about whether Sun-like conditions might support life nearby. Red dwarf stars assault their planets with violent stellar flares capable of stripping away atmospheres over geological timescales. Tidal forces lock these worlds so that one hemisphere experiences eternal daylight, while the other freezes in perpetual darkness. The habitable zones around red dwarfs nestle so close to their host stars that gravitational effects create extreme conditions hostile to life as we understand it. Finding planets around Alpha Centauri A or B would carry vastly more profound implications. These stars genuinely resemble our own Sun in nearly every measurable way. Alpha Centauri A exceeds solar mass by only about 10%. Its radius matches solar dimensions almost exactly. Its surface temperature hovers around 5,790 Kelvin, within 200 degrees of the Sun's 5,772 Kelvin photosphere. Its total energy output surpasses solar luminosity by roughly 50%, but remains firmly within the range we'd call Sun-like. Planets circling these stars would experience genuinely comparable conditions to what Earth receives from the Sun. They'd be warmed by the same type of stellar radiation, bathed in similar spectra of light, subjected to analogous stellar winds and magnetic activity. For the first time, we might study a planetary system that truly mirrors our own cosmic environment. The James Webb Space Telescope was never designed to observe Alpha Centauri. When engineers and scientists conceived this remarkable instrument, they envisioned it studying the most ancient and distant galaxies in the observable universe. The telescope's detectors were optimized for capturing photons that had traveled billions of years across expanding cosmic space before finally reaching the golden mirrors, positioned at Lagrange Point 2, a gravitationally stable location about 1 million miles from Earth. Pointing such an exquisitely sensitive instrument at one of the brightest objects in the night sky seemed not just counterintuitive, but potentially dangerous. The intense light could saturate detectors, create overwhelming glare artifacts, possibly even cause permanent damage to the priceless sensors. The telescope cost approximately $10 billion and required more than 2 decades to design, construct, test, and deploy. Nobody wanted to risk damaging irreplaceable hardware by pointing it at stellar targets it was never meant to observe. The conservative approach suggested sticking to JWST's designed mission profile, studying distant cosmic phenomena where its revolutionary capabilities could transform our understanding of galaxy formation, early stellar populations, and the infant universe. Leave the bright nearby stars to other instruments better suited for such observations. But one astronomer refused to accept this conservative wisdom. Charles Beichmann, a veteran researcher from NASA's Jet Propulsion Laboratory and the NASA Exoplanet Science Institute, had dreamed of detecting planets around Alpha Centauri since long before JWST launched. He assembled a team of like-minded scientists willing to attempt what others dismissed as impossible. Their radical proposal aimed to use JWST's mid-infrared instrument, called MIRI, to hunt for thermal emissions from potential planets orbiting Alpha Centauri A. The concept relied on a clever physics insight. Instead of trying to see reflected starlight bouncing off planetary surfaces, which would be hopelessly overwhelmed by the star's own brilliance, they'd search for heat. Planets absorb radiation from their host stars and re-emit this energy as infrared warmth. A world orbiting in Alpha Centauri A's habitable zone would maintain temperatures between about 200 and 350 Kelvin, cool enough to radiate strongly at mid-infrared wavelengths, where MIRI achieves peak sensitivity. This approach favoured detection of mature planetary systems. Young planets still glow brightly from the residual heat of formation, making them relatively easy to spot in near-infrared observations. But older planets that formed billions of years ago have cooled substantially. Their thermal signatures peak at longer mid-infrared wavelengths, accessible only to specialised instruments like MIRI. Alpha Centauri A has existed for approximately 5 billion years, roughly the same age as our Sun. Any planets circling this mature star would have long since radiated away their formation heat, shining only through absorbed and re-emitted stellar energy. MIRI's 15.5 micrometer filter offered the best chance of capturing these faint thermal signatures. But detecting planetary warmth requires blocking the overwhelming glare from the host star itself. MIRI includes a coronagraph specifically designed for this purpose. This sophisticated optical device places a physical mask over the star's position on the detector, creating an artificial eclipse that suppresses stellar light while allowing fainter nearby objects to remain visible. Coronagraphs work through destructive interference. Light waves from the blocked star combine in ways that cancel each other out, reducing brightness by factors of hundreds or thousands. Meanwhile, light from objects positioned slightly away from the mask's center passes through relatively unimpeded. The contrast between suppressed starlight and preserved planetary light makes detection possible. For most stellar targets observed by JWST, coronagraphs perform beautifully. Stars at typical exoplanet hunting distances present manageable brightness levels, well within instrument specifications. Standard target acquisition procedures lock onto these stars without difficulty. Observations proceed according to established protocols refined through hundreds of successful campaigns. Alpha Centauri shattered every assumption underlying these standard procedures. This system presented a cascade of unique challenges that threatened to doom any observation attempt before it could begin. First, the star moves. Alpha Centauri possesses one of the largest proper motions of any naked-eye star in the sky. It races across the celestial sphere at approximately 3.7 arcseconds per year, covering angular distances visible to careful observers over human lifetimes. This sounds tiny in absolute terms, but it represents significant displacement during the precision observations JWST requires. The telescope must continuously adjust its pointing to keep the star centered precisely behind the coronagraphic mask. Errors of even 10 milliarcseconds degrade coronagraph performance and allow stellar light to leak around the mask edges, flooding the detector. Alpha Centauri's rapid proper motion demanded tracking precision beyond anything previously attempted with JWST observations. Second, the binary companion creates observational chaos that no coronagraph can fully suppress. Alpha Centauri b currently orbits close enough that its brilliant light scatters across the entire detector field of view. No coronagraph in existence can simultaneously block two bright stars positioned at different locations on the detector. Even perfect suppression of Alpha Centauri a's light would still leave massive contamination from its stellar sibling painting artifacts across the entire field. Third, Alpha Centauri A simply exceeds the brightness limits for standard JWST operations. The telescope's fine guidance sensors, which normally lock onto target stars to maintain precise pointing, were never designed to handle objects this luminous. Standard target acquisition procedures that work flawlessly for ordinary stars would completely overwhelm the delicate detectors when aimed at this blazing furnace. Brightness safety limits existed specifically to prevent exactly this type of observation. Fourth, the galactic background creates identification confusion that complicates every measurement. Alpha Centauri lies directly in the plane of the Milky Way, where thousands of faint background stars crowd into every field of view. Any detected point of light might be a planet orbiting Alpha Centauri A, or it might be a distant galaxy billions of light years away that just happens to align with the nearby stellar system through cosmic coincidence. Distinguishing genuine planetary signals from unrelated background sources requires careful analysis that simple detection alone cannot provide. The operations team at the Space Telescope Science Institute confronted what seemed like an impossible task. They needed to develop completely custom observing sequences that had never been attempted with JWST. Standard procedures wouldn't work. Every aspect of the observation required innovation, creativity, and willingness to push the telescope into uncharted operational territory. The solution emerged through months of meticulous planning and simulation. The team developed a technique they called blind offsetting that would bypass the brightness limitations preventing direct target acquisition. Instead of pointing JWST at Alpha Centauri A directly, which would overwhelm the guidance sensors, the telescope would first lock onto a nearby reference star of manageable brightness. They selected Epsilon Muscae, a red giant star located approximately 330 light-years from Earth in the constellation Musca. This distant stellar furnace provided suitable brightness for standard acquisition procedures. The telescope's guidance systems could lock onto Epsilon Muscae without difficulty using normal operational modes that had been proven through countless previous observations. From this reference position, the telescope would execute a precisely calculated offset maneuver to position Alpha Centauri A behind the chronographic mask without ever directly pointing at the target. This blind approach required knowing the exact positions of both stars to accuracies measured in milliarc seconds. The slightest error would place Alpha Centauri A off-center from the mask, allowing stellar light to flood the detector and destroy the observation. The calculations had to account for Alpha Centauri's substantial proper motion. At a distance of only 1.34 parsecs, the star's apparent position shifts by 750 milliarc seconds as Earth orbits the Sun, creating seasonal parallax variations. This parallax motion means the star appears in different positions depending on when you observe it. Coordinates valid in January would place the star in the wrong position by March. The team developed automated software pipelines that computed fresh offset values based on the exact observation date and time. Nothing could be assumed constant when targeting a star that moves measurably against the background sky. Every observation required bespoke calculations incorporating current ephemeris data. The first observation attempts in early 2023 failed completely. Technical difficulties rendered the data entirely unusable. The telescope struggled to maintain precise pointing while compensating for the target's motion and extreme brightness. Coronagraph performance degraded below the levels required for planet detection. Contamination from Alpha Centauri B scattered everywhere, creating overwhelming artifacts. Many research teams would have given up after such comprehensive failure. The difficulties seemed to validate what skeptics had predicted from the start. Alpha Centauri was simply too challenging for JWST to observe productively. The telescope should return to its designed mission studying distant galaxies rather than attempting impossible planetary detections around the brightest nearby stars. But Bateman's team refused to abandon their goal. They regrouped, analysed what went wrong, developed improved strategies addressing each failure mode. They modified, pointing procedures to achieve better centering accuracy behind the coronagraph mask. They created new data reduction algorithms specifically designed to handle contamination from the binary companion star. They tested everything through exhaustive simulations before attempting another observation. In mid-2024, they implemented their refined approach. Test observations demonstrated that the modifications worked. JWST could finally observe this impossible target with sensitivity approaching theoretical performance limits. The team requested and received approval for a full observation campaign targeting Alpha Centauri A. In August 2024, the telescope executed 3 lengthy observation sequences pointed at humanity's nearest Sun-like stellar neighbour. Each exposure lasted hours as the coronagraph blocked stellar light, while detectors patiently collected whatever faint signals emerged from the surrounding space. The team watched data stream back from Lagrange Point 2 with mounting anticipation mixed with anxiety. Had they finally succeeded where so many previous attempts had failed? The raw images showed exactly what astronomers expected from such a challenging observation. A chaotic mess. Contamination from Alpha Centauri B blazed near the top of each frame. Scattered light created bright streaks and halos extending across the entire detector field. The coronagraph produced complex diffraction patterns as stellar light bent around mask edges. No human eye could identify anything meaningful in these raw data products without sophisticated processing. The team employed a method called reference star differential imaging. They observed other similar stars using identical coronagraph configurations to create templates showing how the instrument behaves when no planet exists in the field. Subtracting these reference templates from Alpha Centauri data removed systematic patterns arising from optical effects while preserving genuine astronomical signals unique to the target. Additional algorithms stripped away remaining contamination sources layer by layer. Principle: component analysis and other mathematical techniques identified and removed correlated noise patterns that simple reference subtraction couldn't eliminate. The data reduction process was painstaking, methodical, absolutely crucial for revealing what lay hidden beneath the overwhelming stellar glare, and what emerged shocked everyone involved. At a separation of approximately 1.5 arc-seconds from Alpha Centauri A, a faint point of light appeared in the fully processed images. This object, which the Discovery team designated S1, shone more than 10,000 times fainter than its brilliant host star. Its position placed it roughly 2 astronomical units from Alpha Centauri A, near the outer edge of the star's habitable zone. The detection achieved statistical significance of 5.5 sigma. In scientific terms, this means the probability of random noise creating such a strong false signal drops below 1 in 10 million. Genuine astronomical sources produce signals this strong. Random detector fluctuations essentially never do. Something real had been detected beside our nearest Sun-like stellar neighbour. Rigorous testing followed immediately. The team needed to eliminate every possible alternative explanation before claiming a planetary discovery. Could S1 be a distant background galaxy masquerading as a nearby planet? They cross-referenced the detection position against every astronomical catalogue. Nothing matched. Could it be a foreground asteroid drifting through the field during observations? Motion analysis showed the signal remained stationary relative to Alpha Centauri A. Could it be an instrumental artifact created by complex optical interactions? Injection recovery tests verified they could distinguish real signals from processing artifacts. S1 passed every test designed to expose false positives. The brightness and temperature characteristics suggested a Saturn mass world, containing roughly 90 to 150 Earth masses. The effective temperature appeared around 225 Kelvin, approximately minus 48 degrees Celsius. This frigid temperature placed the object near the outer boundary of Alpha Centauri A's habitable zone, the region where liquid water could theoretically persist on rocky planetary surfaces. Of course, a gas giant cannot support liquid water oceans or terrestrial biology, but gas giants frequently host extensive moon systems. If S1 is real, some of its moons might achieve conditions suitable for life. A Titan-like satellite warmed by a nearby Sun-like star could potentially support surface liquid water, atmospheric chemistry, even biological processes. The August 2024 observation appeared to capture a planet candidate orbiting our nearest Sun-like stellar neighbour. If confirmed through additional observations, this would rank among the most significant discoveries in planetary science history. Decades of searching might finally have succeeded, but the team recognised that a single observation epoch couldn't provide definitive confirmation. Genuine planets orbit their host stars in predictable patterns, governed by gravitational physics. Their positions change over time according to Kepler's laws of planetary motion. Confirming S1 as a real planet rather than some exotic false positive required observing it at multiple times and watching it move along a consistent orbital path. The Space Telescope Science Institute granted directors discretionary time for urgent follow-up observations. This precious resource provides rapid response capability for scientifically critical targets that cannot wait for normal proposal cycles. The Alpha Centauri planet candidate clearly qualified. 2 additional observation campaigns were scheduled for early 2025. February and April observations would capture the Alpha Centauri A system, using techniques identical to the August discovery data. If S1 represented a genuine planet, it should appear at different positions consistent with orbital motion between observing epochs. The amount and direction of movement would constrain orbital period and geometry. The scientific community held its collective breath waiting for results. Rumours circulated through astronomical conferences and online forums. The closest Sun-like star to Earth might actually host a directly imaged planet. A cosmic neighbour that philosophers and scientists had wondered about for centuries might finally reveal its planetary family. The implications extended far beyond simple detection statistics. Alpha Centauri A resembles our Sun in almost every measurable characteristic. Finding a planet here would provide unprecedented opportunities for comparative planetary science, atmospheric characterization, potentially even biosignature searches if habitable moons existed. The February 2025 observations proceeded flawlessly from a technical standpoint. Every system aboard the James Webb Space Telescope performed exactly as designed. The blind offset maneuver placed Alpha Centauri A precisely behind the coronagraph mask. Detectors collected photons for hours while maintaining rock-steady pointing. Data streamed back to Earth at light speed. Scientists activated their analysis pipeline immediately upon data arrival. The same techniques that unveiled S1 in August ground through the February observations with mechanical precision. Reference star subtraction removed systematic artifacts. Principal component analysis stripped away correlated noise patterns. Layer by layer, the contamination peeled away, but nothing appeared. The region where S1 had blazed with 5.5 sigma significance in August showed only empty space in February. No strong detection emerged from the noise. No marginal signal hinted at planetary presence. The planet, candidate, had vanished. Scientists triple-checked their analysis. Perhaps a processing error corrupted the results. They reran pipelines with different parameters. They tried alternative algorithms. They examined raw data directly. Every approach produced identical conclusions. The February observations contained no detectable planet around Alpha Centauri A. The April 2025 observations offered another chance. Perhaps February represented an unlucky epoch where some condition degraded sensitivity. Maybe the planet had moved to an unfavourable position that would improve by April. April data arrived and underwent identical scrutiny. Once again, nothing. The candidate planet had completely disappeared. Whatever JWST detected in August 2024 no longer revealed itself to the most powerful space telescope ever constructed. Aniket Sanghi, a doctoral student at the California Institute of Technology and co-first author on the Discovery Papers, described the bewildering situation perfectly. They faced the case of a disappearing planet. This outcome demanded explanation. Planets don't simply vanish. Gravitationally bound objects follow predictable paths. If S1 represented a genuine world, it should appear somewhere in every observation. 3 distinct possibilities emerged to account for the missing signal. The first possibility was the most deflating. Perhaps S1 was never real. Despite passing every statistical test, the August detection might represent an extraordinarily improbable fluctuation in detector noise that happened to mimic a genuine source. Random processes occasionally produce patterns that seem impossibly unlikely. At 5.5 sigma significance, the probability of such a false positive drops below 1 in 10 million, but extraordinarily rare events do occasionally occur. Perhaps Alpha Centauri became the unlucky target, where random chance conspired to create an illusory planet. The second possibility involved contamination from unknown background sources. Astronomical images capture everything along the line of sight. A distant galaxy or extremely faint background star might have created the signal attributed to a planet. If this background object possessed significant proper motion, it might have drifted away from the detection position by February, explaining both the initial signal and subsequent non-detections. The team exhaustively investigated this scenario. They examined Gaia spacecraft data, which has precisely measured positions for nearly 2 billion stars. No stellar source appeared near the S1 location. They searched archival images from multiple telescopes spanning decades. No background object matched the detected brightness and position. The spectral characteristics remained consistent with a thermal emitting planet rather than a distant galaxy. Every test designed to expose background contamination came back negative. The third possibility offered the most scientifically. Intriguing explanation. S1 might be completely genuine but moved beyond detection limits through simple orbital mechanics. Understanding why a real planet might disappear requires examining how coronagraph sensitivity varies across the field of view. These instruments don't provide uniform detection capability everywhere around a blocked star. Physics conspires to make some regions highly sensitive while rendering others effectively blind. Coronagraph masks suppress starlight by covering the central stellar image, but diffraction fundamentally limits how completely any physical object can block electromagnetic radiation. Light bends around edges. When starlight encounters the mask boundary, some fraction diffracts around rather than being blocked. This diffracted light creates complex patterns extending outward from the mask's position. Close to the star, diffracted contamination overwhelms any planetary signals. Only at certain angular separations does sensitivity reach levels capable of detecting the extreme contrast ratios required for planet imaging. Too close and diffraction dominates, too far and the planet becomes too faint. A narrow sweet spot exists where detection becomes possible. Additionally, coronagraph sensitivity varies dramatically with position angle around the blocked star. The 4-quadrant phase mask used by MIRI creates different suppression levels in different directions. Some position angles achieve excellent contrast while others remain hopelessly contaminated. A planet might shine clearly when positioned along one direction from its star, then disappear entirely when orbital motion carries it to an unfavourable angle just months later. If S1 follows an elliptical orbit rather than circular, its distance from Alpha Centauri A changes continuously. At some phases it might approach too close for detection. At others, it might pass behind or in front of the star from Earth's perspective, hiding through geometric alignment. The research team tested this hypothesis through sophisticated orbital simulations. They generated millions of possible orbits with varying periods, eccentricities, inclinations, and orientations. Each had to satisfy physical constraints, including gravitational stability given Alpha Centauri B's presence. The simulations incorporated tantalizing information from an earlier observation. In 2019, astronomers using the European Southern Observatory's Very Large Telescope captured a faint signal near Alpha Centauri A using a ground-based infrared instrument. This marginal detection, designated C1, appeared at approximately 1.1 astronomical units from the host star, but could never be confirmed due to atmospheric limitations. What if C1 and S1 represented the same object observed at different orbital phases 6 years apart? A planet on an eccentric orbit would appear at different distances depending on when observed. If this hypothesis held, combining both detections would dramatically constrain possible orbits. The computational results stunned the team. Their models found that 52% of gravitationally stable orbits fitting the combined astrometric positions would naturally produce non-detections in both February and April 2025. These orbits carried the planet to regions where JWST's coronagraph sensitivity dropped below detection thresholds during exactly those months. This statistical finding transformed everything. Rather than contradicting the planetary hypothesis, the non-detections actually remained consistent with S1's existence. More than half of allowed orbits would be invisible in early 2025 and visible again at some future date. The absence of detection provided no evidence against the planet's reality. The disappearing planet wasn't violating physics. It was behaving exactly as orbital mechanics predicted. The surviving orbital solutions painted a picture of an unusual planetary system. S1 appears to follow a significantly eccentric orbit, where its distance from Alpha Centauri A varies dramatically. Current estimates suggest eccentricity around 0.4, meaning the closest approach distance is only about 60% of maximum separation. Compare this to our solar system. Earth follows an almost perfectly circular orbit with eccentricity below 2%. Mars reaches 9%. Mercury holds the record among major planets at 21%. S1's estimated 40% eccentricity exceeds anything in our planetary neighbourhood, except certain dwarf planets and comets. The orbital period falls somewhere between 2 and 3 Earth years based on current constraints. At perihelion, the planet passes within roughly 1 astronomical unit of Alpha Centauri A, similar to Earth's distance from the Sun. At aphelion, it retreats nearly 2 astronomical units, approaching Mars's orbital radius. This wide swing creates the visibility pattern explaining both detections and non-detections. When approaching perihelion, S1 moves too close for coronagraph detection, hiding in stellar glare. When retreating toward aphelion, it emerges into regions where Miri achieves sufficient sensitivity. August 2024 apparently captured S1 near aphelion. By early 2025, it had moved toward perihelion where current technology cannot see it. The planet didn't vanish. It simply moved to an orbital phase beyond detection capability. Perhaps most surprising is the orbital inclination. The path appears tilted roughly 50 degrees relative to the Alpha Centauri binary orbital plane. This substantial misalignment suggests either unusual formation conditions or subsequent gravitational evolution that tilted an initially aligned orbit. Planet formation models generally predict that worlds inherit angular momentum from parent protoplanetary disks, typically aligning with stellar orbital planes. Finding significant misalignment challenges standard scenarios. Alternative explanations invoke gravitational perturbations from other planets subsequently ejected, or long-term interactions with the binary companion gradually pumping inclination through resonance effects. Despite the unusual geometry, stability calculations indicate S1's configuration remains gravitationally bound for billions of years. The planet survives because it never ventures close enough to Alpha Centauri B for disruption. At 2 astronomical units maximum separation from Alpha Centauri A, it remains safely within the primary star's gravitational sphere of influence. The research team documented their findings in 2 peer-reviewed papers accepted for publication in astrophysical journal letters, one of astronomy's most prestigious journals. The first presented observational details, detection characteristics, and orbital analysis. The second described sophisticated image processing methodology and sensitivity characterization. Both papers carefully emphasize that S1 remains a candidate planet rather than confirmed detection. A single robust observation epoch cannot definitively prove planetary nature regardless of statistical significance. Confirmation requires tracking the object through multiple orbital phases and demonstrating motion following gravitationally bound trajectories. The papers thoroughly addressed alternative explanations. Could S1 be a dust cloud? Circumstellar debris from asteroid collisions occasionally appears as point-like signals before dispersing. Brightness and colour characteristics remain consistent with either planetary atmospheres or concentrated dust clouds. Distinguishing requires additional multi-wavelength observations. Could it be a brown dwarf? These failed stars occupy the mass range between giant planets and hydrogen-fusing stars. Mass estimates suggest S1 falls firmly in the planetary regime rather than brown dwarf territory, which typically exceeds 13 Jupiter masses. Could multiple smaller objects collectively produce the signal? The team considered this but found it statistically less probable than a single planet based on observed brightness distributions. The scientific community received findings with appropriate mixture of cautious skepticism and palpable excitement. The case rests on a single detection epoch supported by theoretical arguments explaining subsequent non-detections, but if confirmation arrives, S1 would simultaneously claim multiple historic records. It would become the closest exoplanet to Earth orbiting a sun-like star. Proxima Centauri's planets lie slightly closer in raw distance but orbit a fundamentally different stellar type. It would become the nearest directly imaged exoplanet by substantial margin. It would become the oldest directly imaged exoplanet by an enormous factor, as previous successes targeted young stellar associations. It would become the coldest directly imaged exoplanet, as young hot planets dominate current samples. It would orbit closest to its host star of any directly imaged exoplanet. These superlatives explain continued enthusiasm despite challenging observations and frustrating disappearance. Orbital models make specific predictions about when S1 should return to detectable positions. Based on stable orbits consistent with current constraints, the planet should approach aphelion again in mid-2026. August 2026 represents the most probable window for redetection. If JWST observes Alpha Centauri A during this predicted window and detects S1 near expected position, the case for planetary confirmation becomes overwhelming. A third detection matching orbital predictions would essentially prove a gravitationally bound object orbits our nearest sun-like stellar neighbour. If August 2026 observations fail despite favourable geometry, the mystery deepens. Either the planet follows orbits outside current models, requiring parameter revision, or the original detection truly was a remarkably improbable statistical fluctuation. If S1 exists as the data suggests, what would this world actually be like? The confirmed measurements from August 2024 provide our best estimates, though every number carries substantial uncertainty. The planet appears to be a gas giant comparable to Saturn. Mass estimates place it around 90 to 150 Earth masses. Saturn contains 95 Earth masses for comparison. The radius likely falls between 1 and 1.1 Jupiter radii, meaning physical size roughly matches Jupiter despite containing less mass. This combination implies bulk density lower than liquid water, confirming hydrogen-helium-dominated composition consistent with giant planet formation. The effective temperature of approximately 225 Kelvin makes S1 considerably warmer than Saturn's 134 Kelvin cloud tops. The temperature difference arises from Alpha Centauri A's greater luminosity compared to our Sun, plus potential internal heat generation from gravitational contraction and radioactive decay. The atmospheric composition remains entirely unknown. Current observations detected thermal emission without spectroscopic measurements identifying specific molecules. Future observations using JWST's spectroscopic capabilities might reveal methane, ammonia, water vapor, or other compounds expected in gas giant atmospheres. Saturn's atmosphere contains hydrogen, helium, methane, ammonia, and trace complex hydrocarbons. S1 likely hosts similar chemistry, modified by different stellar spectrum and warmer temperatures. But atmospheric chemistry represents only part of what makes S1 scientifically fascinating. The planet's location within Alpha Centauri A's habitable zone creates extraordinary possibilities. The habitable zone describes the circumstellar region where rocky planets could maintain liquid water on surfaces. S1 orbits within this zone, spending most of its eccentric path where temperatures on rocky worlds could support liquid water. The gas giant itself obviously cannot host surface oceans or biology. It lacks solid ground. But giant planets rarely travel alone. Every giant in our solar system hosts extensive moon systems. Saturn possesses more than 270 known moons. The largest Saturnian satellite, Titan, exceeds Mercury in diameter while maintaining dense nitrogen atmosphere. Liquid methane and ethane pool into seas covering portions of Titan's surface. Complex organic chemistry occurs continuously. Enceladus, a smaller moon, conceals global subsurface ocean beneath icy exterior. Geysers erupting from south polar fractures spray water vapor into space. Scientists consider Enceladus among the most promising locations for extraterrestrial life in our solar system. Jupiter's moon Europa hosts similar subsurface ocean, estimated 100 kilometers deep beneath ice shell. Tidal heating from Jupiter's gravitational field maintains liquid water despite surface temperatures hundreds of degrees below freezing. Ganymede and Callisto likely contain subsurface water layers sandwiched between ice and rock. If S1 follows patterns established by Jupiter and Saturn, it should host extensive satellite systems. Planetary formation models suggest moon systems arise naturally as circumplanetary disks condense into satellites. Some hypothetical moons might achieve conditions suitable for liquid water. A moon orbiting S1 within Alpha Centauri A's habitable zone would experience surface temperatures moderated by stellar radiation. Unlike frozen outer solar system moons relying entirely on internal heat, moons around S1 could potentially support surface liquid water warmed by nearby Sun-like star. Imagine a Titan-like moon, but warm enough for liquid water rather than methane. Rivers and lakes could form through familiar hydrological cycles. Atmospheric chemistry might produce conditions recognizable to terrestrial organisms. Life could emerge through processes analogous to Earth's biosphere origins. This scenario transforms gas giant detection into potentially habitable real estate discovery. We cannot observe moons around S1 with existing technology. Angular separation between planet and hypothetical satellites would be far too small to resolve, but their existence follows naturally from planetary formation understanding. The possibility of habitable moons orbiting our nearest Sun-like stellar neighbour carries profound implications for astrobiology. If S1 hosts moons and any achieve habitable conditions, then life might exist merely 4 light-years from Earth. That distance represents something future technology might actually traverse. Breakthrough Starshot and similar initiatives propose launching small spacecraft at relativistic velocities using laser propulsion. These probes could reach Alpha Centauri within 2 decades of launch, returning observations within human lifetime. Knowing potentially habitable moons await transforms speculative engineering into motivated mission planning. Broader scientific implications. Beyond individual planetary detection, the S1 discovery carries implications extending throughout multiple fields of astronomical research. The sensitivity achieved during Alpha Centauri observations established new benchmarks for direct imaging capabilities. Consider the exozodiacal dust measurements emerging from same data. Zodiacal dust consists of microscopic particles from asteroid collisions and cometary activity. In our solar system, this dust creates faint glow visible along ecliptic plane before sunrise and after sunset. If Alpha Centauri A hosted dense debris disk, scattered starlight might overwhelm planetary signals. The JWST observations constrained any zodiacal dust around Alpha Centauri A to levels only 5 to 8 times brighter than solar system conditions. This represents the most sensitive exozodiacal measurement ever achieved around any star besides the Sun. Previous observations could only constrain debris to levels tens or hundreds of times brighter. For the first time, astronomers can meaningfully compare another star's dust environment to our cosmic neighbourhood. Relatively low debris levels suggest mature planetary system settled into dynamical equilibrium after billions of years. Dense debris typically indicates recent collisional activity. Finding Alpha Centauri A lacks excessive debris provides encouraging news for habitability prospects. The contrast ratio achieved deserves emphasis. Detecting signals 10,000 times fainter beside overwhelming glare pushes chronography to fundamental limits. Imagine photographing candle flame beside lighthouse beam from Los Angeles to New York distance. JWST accomplished the astronomical equivalent. The angular separation of 1.5 arcseconds represents the smallest planet-to-star separation ever achieved for directly imaged exoplanet candidates. Previous discoveries captured planets tens or hundreds of arcseconds from host stars. Greater separation reduced contamination. S1 challenged astronomers to push much closer towards stellar glare than any previous target. Binary star systems were long considered hostile environments for planetary formation and survival. Gravitational interplay between stellar companions disrupts protoplanetary disk material before planets coalesce. Alpha Centauri presents a particularly challenging case with main stars approaching within 11 astronomical units. Computer simulations consistently predicted planet formation should be suppressed in such tight configurations. Previous theoretical work identified narrow stability zones where planets might barely survive. Close orbits within 1 to 2 astronomical units appeared marginally stable against long-term disruption. S1 apparently occupies exactly this marginal zone, threading the needle between regions too close for detection and too distant for stability. The planet exists precisely where theory predicted worlds might barely survive. But orbital inclination poses additional challenges. Substantially misaligned planets require explanation. Several formation scenarios could produce observed configuration. Perhaps S1 formed in aligned orbit subsequently tilted through gravitational interactions with other now absent planets. Perhaps it formed elsewhere and migrated through disk interactions. Perhaps the system experienced dynamical instability rearranging architectures. Each scenario generates testable predictions. Finding additional planets would support multi-body interaction models. Detecting systematic orbital variations would indicate ongoing evolution. Precise binary parameter characterization might reveal past dynamical settling signatures. Broader implications ripple throughout galactic planetary science. Approximately half of Sun-like stars reside in binary or multiple systems. If planets form and survive around Alpha Centauri despite tight companion, similar worlds might populate countless other binaries previously dismissed as hostile to formation. Conservative estimates suggest 200 billion stars populate our galaxy. If half exist in binaries, 100 billion binary systems await investigation. Even if only 10% host planets, 10 billion worlds orbit binary pairs throughout Milky Way. Some fraction might occupy habitable zones, supporting liquid water and potentially life. Adding binary planets to galactic census dramatically increases potentially habitable real estate estimates. Single-star systems already host billions of Earth-like worlds based on Kepler statistics. Binary populations might double or triple total habitability estimates, fundamentally reshaping how common life-supporting environments might be cosmically. While JWST pioneered Alpha Centauri observations, next-generation telescopes will revolutionize our ability to study this system and similar nearby targets. The extremely large telescope under construction in Chile's Atacama Desert will possess 39-meter primary mirror when achieving first light. This enormous aperture exceeds existing optical telescopes by a factor of 4, providing correspondingly improved resolution and light-gathering capability. Its coronagraph instruments will push contrast ratios and inner working angles beyond current space-based performance. The 30-meter telescope planned for Mauna Kea offers similar revolutionary capabilities through segmented primary mirror rivaling the ELT. The giant Magellan telescope combines 7 8.4-meter mirrors into coherent array with 25-meter equivalent diameter. Within a decade, these instruments will observe Alpha Centauri with sensitivity exceeding JWST's performance by substantial margins. If S1 is real, ground-based telescopes will track orbital motion with sub-milliarc-second precision impossible from space platforms. If additional planets exist, larger apertures and improved coronagraphs will detect them. These facilities enable moon searches around S1. While JWST lacks resolution to detect satellites, extremely large ground-based telescopes might achieve angular precision. identifying large moons orbiting far enough to resolve as separate sources. Titan-sized satellite would produce detectable signals if orbiting sufficiently far from S1. The Nancy Grace Roman Space Telescope launching mid-2020s includes coronagraph technology, demonstration testing starlight suppression beyond any operational system. While Roman's primary science involves wide-field surveys, its coronagraph will prove concepts essential for subsequent dedicated missions. The Habitable Worlds Observatory, recommended by recent astronomy decadal survey, would directly image Earth-like planets around nearby stars for first time. This ambitious mission incorporates lessons from JWST, Roman, and ground-based demonstrations. Technology pathfinder observations at Alpha Centauri directly inform habitable worlds designs. Finding planets around Alpha Centauri transforms interstellar mission planning from speculation to focused development. Breakthrough Starshot proposes launching gram-scale spacecraft toward Alpha Centauri at relativistic velocities using ground-based laser propulsion. These concepts imagine pushing tiny probes to 20% light speed, enabling arrival within approximately 21 years. Such missions seemed pointlessly speculative when we knew nothing about destinations. Why invest billions and decades visiting potentially barren systems? Uncertainty undermined enthusiasm for interstellar concepts. Knowing planets exist changes calculations fundamentally. Mission designers incorporate specific objectives based on known characteristics. Observation strategies target predicted positions from refined models. Instrument specifications emphasize measurements most relevant to understanding actual system contents. Possibility of habitable moons amplifies motivation. If Titan-like satellites orbit within habitable zone, close-up observations could search for biosignatures impossible detecting from Earth's distance. Atmospheric spectra might reveal oxygen, methane, or gases indicating biological activity. Surface imaging might show liquid water features or vegetation signatures. Even without biological detections, close-range planetary observations would revolutionize comparative planetology. We currently know gas giants only from 4 solar system examples, plus distant exoplanets observed through limited techniques. S1 would provide 5th detailed case study formed in an entirely different stellar environment, comparing atmospheric structure, magnetic field configuration, satellite system and ring properties against. Jupiter and Saturn would reveal how characteristics depend on formation conditions and evolutionary history. Within single human lifetime, we might receive close-up observations from another stellar system resolving questions about habitability, remaining forever ambiguous from Earth-based telescopes. No other target allows such prompt investigation with foreseeable technology. The implications extend to fundamental questions about life in the universe. The Drake equation famously estimates technological civilizations existing in our galaxy. Frank Drake formulated this framework in 1961, organizing thinking about extraterrestrial intelligence. The equation multiplies factors including star formation rate, fraction hosting planets, fraction where life emerges, and terms describing intelligence and technology development. Before exoplanet revolution, astronomers debated intensely whether planets existed around most stars or only rare configurations. Discovery of thousands of exoplanets settled this decisively. Planets are ubiquitous. Nearly every star possesses at least one companion. The planetary frequency term approaches unity. Worlds are everywhere. But Drake equation terms involving life remained purely speculative. Despite planetary abundance, we possess exactly one example of life emerging. That single data point tells us almost nothing about how common biological genesis might be. Finding potentially habitable environments around nearest sun-like neighbour changes how we approach uncertainty. If Alpha Centauri hosts moons where liquid water could exist, the closest stellar system offers opportunities distant targets cannot match. Spacecraft travelling 20% light speed would reach Alpha Centauri in 21 years. Adding transmission time extends total to 25 years. Within single human lifetime, we might receive observations resolving habitability questions, remaining ambiguous from Earth-based telescopes. Alpha Centauri represents humanity's only realistic destination for interstellar probes within coming century. Everything about this system matters enormously, because we might actually visit within timescales relevant to human planning. The detection carries philosophical weight extending beyond scientific investigation into questions about human identity and cosmic significance occupying thinkers throughout recorded history. For all human existence until recently, stars represented unreachable lights decorating night sky. Ancient cultures created mythologies around stellar patterns seeming eternal and unchanging. The cosmic sphere appeared fundamentally different from terrestrial realm where human lives unfolded. Modern astronomy beginning 4 centuries ago revealed stars as distant suns, nuclear furnaces generating light through thermonuclear fusion operating according to same physical laws governing earthly phenomena. Same quantum mechanics explaining laboratory spectroscopy also explains stellar atmospheres billions of miles distant. Exoplanet revolution, 3 decades ago, extended unification to planetary systems. Worlds similar to and vastly different from those orbiting our sun circle, countless other stars. Gravitational collapse, disk formation, and planetary accretion creating Earth operate everywhere stars form. These discoveries transformed understanding of cosmic organization. We learned planets are common, perhaps nearly universal. Statistical extrapolation suggested billions of potentially habitable worlds scattered throughout Milky Way. Loneliness implied by cosmic vastness softened with recognition. Countless other worlds might support life emergence. But exoplanet statistics remained abstract. We knew planets existed in aggregate without knowing details about specific individual worlds around particular nearby stars. Our nearest sun-like neighbour guarded planetary secrets behind impenetrable glare. Now we detect specific planet around individual nearby star. Abstraction of population statistics collapses into concrete reality. That particular point of a light visible tonight apparently hosts planetary system, including at least one gas giant orbiting within habitable zone. This personalization transforms understanding our relationship to universe. We are not merely observers cataloguing anonymous populations across unimaginable distances. We are neighbours in cosmic community. The 4.37 light-years seems somehow less isolating when we know what awaits across Gulf. Distance remains enormous by human standards. Travel time prohibits visitation with current technology. Communication delays render conversation impossible, but Gulf has transformed from infinitely vast in practice to merely very large in principle. Barrier is technological rather than fundamental. Nothing prevents eventual crossing. Challenge lies in engineering rather than impossibility. Science fiction writers imagined Alpha Centauri as humanity's first interstellar destination for generations, placing alien civilizations and habitable worlds without observational evidence. System became shorthand for interstellar aspiration because proximity suggested achievability. Now, fictional speculations edge toward observational reality. We cannot yet confirm alien civilizations or habitable moons, but we can confirm at least one. Planetary candidate orbits our nearest sun-like neighbour. Imagined destination has begun revealing actual nature through patient photon accumulation. Universe reveals secrets gradually to species developing tools capable of asking questions, and patients awaiting answers. Humanity wondered whether planets orbit Alpha Centauri since understanding stars might host worlds. That wondering persisted through centuries of technological development, progressively improving our ability seeking answers. JWST represents culmination of decades of effort by thousands of scientists and engineers who designed, built, tested, launched, and now operate the most powerful astronomical observatory ever constructed. Their work produced first meaningful answer to questions haunting previous generations lacking investigation tools. That answer remains provisional. Confirmation awaits future observations during predicted visibility windows. The 2026 campaign will either verify S1's existence or deepen mystery of apparent disappearance. Either outcome advances understanding while generating new questions, but regardless of what 2026 reveals, JWST has proven Alpha Centauri's planetary system can be explored from Earth. Observational barriers protecting system secrets throughout all prior human history have finally yielded to ingenuity, persistence, and engineering excellence. Whatever worlds populate nearest stellar neighbourhood, we now possess tools capable of detecting them. Fireflies hovering beside cosmic searchlight have finally revealed themselves to patient observers, willing to push technology beyond nominal design parameters. Closest sun-like star to Earth no longer maintains perfect privacy. Its planetary companions, whether one or many, whether confirmed or merely suspected, have begun emerging from stellar glare, hiding them since first humans looked upward and wondered. A gas giant world may orbit Alpha Centauri A's habitable zone. That world may host moons where liquid water pools beneath alien skies, illuminated by two suns tracing slow orbital ballet. Life may have emerged on those moons through processes echoing what occurred on Earth billions of years ago. Or the system may prove barren, sterile worlds devoid of conditions biology requires. Either answer represents profound knowledge worth effort obtaining. Either outcome informs humanity's understanding of our place in cosmos, increasingly revealing itself as filled with worlds beyond counting. JWST has cracked open door sealed throughout all previous human existence. What lies beyond awaits patient observation accumulation, eventually resolving mystery into knowledge. The August 2026 observation window approaches. Universe already knows whether S1 will reappear at predicted position, or remain hidden despite favourable geometry. We simply await light carrying that answer across 4.37 light-years of emptiness to detectors waiting in darkness beyond Earth's atmosphere. Whatever that light reveals, the search will continue. Other nearby stars await similar investigation. Other planetary systems will yield secrets to telescopes even more powerful than JWST. Cosmic neighbourhood seeming forever unknowable has begun transforming into territory we can systematically explore and eventually understand. The impossible observation has been achieved. Nearest sun-like star has revealed at least one planetary candidate to instruments pushed beyond design limits by determined scientists refusing to accept some targets was simply too difficult. That achievement cannot be reversed regardless of what future observations reveal about S1 specifically. Humanity has looked into Alpha Centauri and discovered that planets almost certainly orbit there, exact number, masses and configurations await determination through continued investigation. But fundamental question motivating generations of astronomers has finally received answer. Our nearest stellar neighbour hosts worlds of its own. Cosmic loneliness Earth might have experienced as only inhabited world in vast sterile universe grows slightly less acute with every planetary detection around nearby stars. Whatever S1 ultimately proves to be, the detection represents milestone in human understanding that future generations will remember as moment Alpha Centauri finally yielded to our persistent wondering. Stars are not merely lights in sky, they are suns with planets of their own, and closest ones are finally revealing themselves to observers patient and clever enough to seek them out. The story of S1 is far from over. In the coming months, as we approach that critical August 2026 observation window, the astronomical community waits with anticipation to see if this mysterious world will reappear from its hiding place behind the stellar glare. Will the planet emerge at exactly the predicted position, confirming that we've discovered a Saturn-mass world orbiting in the habitable zone of our nearest sun-like neighbour? Or will the mystery deepen, forcing us to reconsider everything we think we know about this detection? One thing is certain. We are living through a pivotal moment in the history of planetary science. The James Webb Space Telescope has opened a window into our cosmic neighbourhood that previous generations could only dream about. Whether S1 turns out to be a genuine planet, a system of moons potentially harbouring life, or simply a phantom signal that taught us valuable lessons about the limits of our technology, we are closer than ever before to answering the ancient question that has haunted humanity since we first looked up at the stars and wondered, are we alone? The universe is revealing its secrets, one photon at a time. And Alpha Centauri, our nearest stellar neighbour, is finally beginning to share what it's been hiding all along. The age of interstellar exploration may be closer than we think, and it all starts just 4 light-years away, with a mysterious signal that appeared, vanished, and might just reappear to change everything we thought we knew about our place in the cosmos. If you want to stay updated on this developing story and witness what might be the most significant astronomical discovery of our generation, make sure you're subscribed with notifications turned on. The verdict is coming in August 2026 and you won't want to miss it. This has been the incredible story of the disappearing planet at Alpha Centauri. Thanks for watching, and I'll see you in the next video where we continue. exploring the mysteries of our universe.